Today's afternoon talk will be by Amritanshu Prasad. He is a professor in the maths department of our institute, and he'll be talking something on Euclid's algorithm. Let's welcome.
Thank you, Kamalaksha, and I'd like to thank all the volunteers who have organized this event, and it's always a bit intimidating to talk to people so young. I'm used to talking to much older people, so I may also talk a bit fast sometimes or use words which you don't know, in which case you must stop me and ask me, hey, what does that mean? Okay? Yeah. And I'm going to talk about old stuff. Mathematicians like old stuff. How old? It goes back to a mathematician, I'm sure you've heard of him, Euclid of Alexandria. He was probably educated in Athens, but he founded a school of mathematics in Alexandria. He flourished around 300 years before Christ, so that's 2,300 years before now, very, very long time ago. And he wrote a textbook, well, it's not just geometry as you'll see, it's a textbook of mathematics, which they weren't his own results, but he collected the results of a lot of earlier and contemporary mathematicians. He also had contributions of his own to these things, but the amazing thing about the elements is the organization and the way it's written. If you want to get an idea of the timeline here, Euclid, we don't know exactly, but he used to have flourished around 300 BC. 300 BC, that's a time when in South India it's not much is known about the history, but Arthashastra was written around that time, and Alexander invaded Sindh in 326 BC. Chandragupta Maurya founded the Mauryan Empire in 322 BC, so this is what's happening in India. Ashoka reigned 273 BC to 232 BC. Sanchi, the stupa, was probably built sometime around then. This is really, really very long ago. Here you see well, I mean, this is probably just an artist's impression of what Euclid looked like. This is a detail from a fresco by the Renaissance painter Raphael this is the Renaissance time in Italy, 1510. The first English edition of, so the story of this book itself is a long and interesting one, which I won't really go into. There's a long story to how the versions that we have today reached us. I mean, it's such an old book, manuscripts were destroyed, finally it came through Persia to us. The first English edition was published in 1570 by Billingsley. But nowadays you can go to the shop and buy this. These are my copies of Euclid's Elements. So you can see there are 13 books, and then 3 volumes. This is a very popular translation by Sir Thomas L. Heath. And this is more or less standard. There have also been many versions for school children. It was very standard to sort of torture school children with geometry books. So when I was in school, I read this book by Hall and Stevens, and that was what actually got me interested in mathematics. So to me, my first introduction to real mathematics was through Euclid. And so reading Euclid is to a mathematician something like, what a Buddhist may be going on a pilgrimage to Sanchi. There's also an online edition created by Joyce, and this is, I think it's based on Heath's translation. So it's got some Java stuff and so on, where the pictures, it's very convenient for quick reference. And I'm hoping that this talk will encourage some of you to look at this book. And what's amazing is, after all these years, this book is still so exciting and interesting to us. Mostly what is taught to school children is the stuff on triangles and similarity and so on. I'm going to take a slightly different direction, and I'm going to talk about some things that are in the 10th book of Euclid, which is about rational and irrational numbers, finding common measures, things like that. So I hope that most of you will find something a little different from your textbooks here, but these are things which you have studied in some other form. I just want to bring a slightly different perspective. The mathematical historian Carl Boyer says that the Elements of Euclid not only was the earliest major Greek mathematical work to come down to us, but also the most influential textbook of all times. I think it's actually much more than a textbook. The method, Euclid's method, what he does is he starts with a small set of basic self-evident axioms of geometry, which are still in your textbooks, I think. And everything in the book is deduced just from these axioms. This is slightly problematic because he takes some notions as primitive and everybody is supposed to understand what they mean. Nowadays mathematicians like to be a little more careful, but still this basic method of having axioms and deducing all of mathematics from these few results remains the way that mathematicians work. So, but the axioms used by mathematicians today are different and are based on a careful analysis of language as well. So, what will we do in this lecture? So, we will revisit an algorithm which I am sure most of you know for finding the GCD or the HCF, the greatest common divisor or highest common factor. I don't know which one is used in your textbooks. HCF, okay, of two numbers. But don't worry, I won't use either. So we'll understand its relation to finding a common measure. So these two sticks you have, what you'll be doing is you'll be trying to find some length that measures both of them. Okay, that's the goal. And we'll also use these ideas to understand the notion of irrational numbers. And at the end of this talk, we'll see a proof that the square root of 2 is irrational, which maybe if some of you have seen a proof, this may be a bit different from the proof you've seen. Let's see. The arrangement of ideas is from Euclid, I mean Euclid's Elements, but I'm not going to do the Euclid style of saying I say let AB be a line and so on. I'm just going to talk about the ideas, and if you're interested, well, Euclid's Elements are easily available and you can go ahead and plunge into it and spend many years of your life enjoying this book. So let's just start with the first definition from Book 10 of Euclid. So this definition says it's about what it means for two magnitudes to be co-measurable. That means you can measure them using the same measure. What is a measure? A measure is essentially a unit of measurement, and when you say you can measure something with that measure, it means that it's an exact whole number of multiples of that measure. So if your measure is an inch, then something is measurable by inches if it is exactly 5 inches or 10 inches. But if it is 10.5 inches, then it's not measurable by inches. Let's just illustrate this. So so the definition says that those magnitudes are said to be commensurable which are measured by the same measure, and those incommensurable which cannot have any common measure. So what does it mean to be measured by a measure? So let's take this line segment A, which will be our measure, and let's take this line segment B, which we'll try to measure using A. Okay, so what we'll do, we'll start measuring. So we'll mark off length A along B, right? And then, well, there's still quite a lot of B left, so let's mark off another length A along B, and let's mark off another length A along B, and we keep doing that, and after we do it 7 times, B is exhausted. So we have measured B using A. So what we are saying is that the magnitude A measures the magnitude B, and you could write B is 7 times A. Okay, but now let's look at another magnitude C. If we try to measure it by A, oh, A also measures C. Okay, so C is 4 times A. So A is a common measure of B and C. On the other hand, if you take D, this is actually 2 times A, then D goes into B 3 times, but then there's something left. So D does not measure B, but D goes into C 2 times, there's nothing left. So D actually measures C. So C measures D, but not C. So it's not a common measure of B and C. And the notion of commensurability is related to the idea of a rational number. The relationship is given by this theorem. If magnitudes A and B are commensurable, then the not ratio A over B is a rational number. Why is that? Well, let's give a proof. So suppose C is a common measure of A and B. That means C goes into A integer number of times, right? So A is m times C for some number m, some whole number n, and B is n times C for some other whole number n. So the ratio and m, so m and n are integers, and so the ratio A by B is mc by nc, which is m over n, which is a rational number by definition. Okay, let's not worry about division by 0 and such things, you know what I'm talking about. Okay, but what happens when B doesn't measure A? Well, we'll try to measure it once, twice, maybe we can squeeze in another B, thrice. Now there's this annoying part left, let's call it C. Okay, so this is yeah, so A is 3B plus C. And this C is a new thing, so usually you would call 3 the quotient and C the remainder. And the nice thing about C is it's strictly smaller than B. So C goes into B. And now we can try to measure B using C if we like. Okay, so what we get is B is actually 3 times C. What does this say about A? Well, we can take this 3 times C and substitute it here, and we get A is 10C. So, what's the upshot of this? B is 3C and A is 10C. So C measures both A and B. So we found a common measure of A and B. This is an example of Euclid's algorithm. So this is exactly Euclid's algorithm. Let's just do one more example. So the idea is simple. You have 2 lengths. You take the shorter one and see how many times it goes into the longer one. And then it will go a certain number of times, but then there may be something left. If there's nothing left, you stop. But there may be something left. So if there's something left, now you take that as your new shorter length, and the old shorter length you make it your longer length, because what's left will be shorter than the first shorter length. So the C is definitely less than B, because if it were greater than or equal to B, we could put B in one more time here. And so you keep doing this each time, getting a new set of short length and long length, till the process ends, if it ends. We will see that it need not always end, it can go on indefinitely. So, so here let us do another example, and this is what you will be doing with your sticks as well, so pay attention closely. So here I have actually I started by calling the shorter length B and the longer length A, somehow the equations look better that way. So we have this B and A, let us try to find a common measure for B and A. So from the picture it is not at all clear what that would be, but what we will be able to do is we will be able to find a common measure, and we will also be able to calculate the ratio A is to B. So we will put B into A, well there is something left, but that is not quite large enough to accommodate another B. So that's, we will call that C. And so what's this picture saying? This picture is saying that A is just B plus C. So let's write down that equation and remember it. I mean it's written down here, so I'll bring it back to this slide after the talk if you want. Okay, so now what you do is you take this C. So this C, now this C is shorter than B, that's something we certainly know, right, because we can't take out B again. So C is shorter than B, so we can try measuring B using C, and again it goes in only once, and again something smaller than C is left, okay. So now we will call that D, and what are we saying? We are saying that B is C plus D. Now what should we do? Let us try to measure C using D. So there I go put in D once, twice, and there is something left. So what we call that? E. And hopefully you know it will be done before 26 steps, otherwise we will have to use Tamil letters. Let us see. So now what do? We got E, we measure D using E. Oh, and wow, 2 times E is D. So now we have got these 4 equations. A is B plus C, B is C plus D, C is 2D plus E, and D is 2E, and Euclid's algorithms ended. We have got a perfect match for D as 2 times E. Now let us work backwards from this, starting with the last equation. D is equal to 2E. We can substitute that in the previous equation, and we get C is 5E. And now we substitute the values of C and D in the previous equation, 12E. So what do we get? We get that D is, so we get that A is 12E and B is 7E. So this E is the common measure, and the ratio of A to B is 12:7. Okay, so this is what Euclid's algorithm gives us. It gives us the common measure and it gives us the ratio. Now the way it's taught usually in modern textbooks is as a result in number theory. So it says that you find the GCD of 2 integers, and so somehow we already know that they are both integer multiples of 1, but we want to find the largest multiple. But this is kind of a more geometric viewpoint, and in that case you already know the ratio. In this case you need not know the ratios, you may just be given 2 broomsticks as I have arranged here in this talk. Okay, so let's just start with those equations again from the previous slide, and we'll fool around with them a little bit. So we had 4 equations. A is B plus C, and we know that B doesn't go into A more than once, so C must be less than B, and B is C plus D, and again we know that D must be less than C, and C is 2D plus E, so we know that, and we know that D doesn't go any more times into C, so E is less than D. Let me just remind you where these are coming from, and finally D is 2E. So that's these steps, right? So we put B into E, we got this C which is strictly less than B, we got D which is strictly less than C, and we got E which is strictly less than D, and we got, well, d is 2e, and the process stopped there. So, so the equation 1, we can think of it as a statement about the ratio a over b. So what does it say about a over b? Well, basically we are just taking the first equation, dividing it by b. It says that a over b is 1 plus c over b, and this fact that c is less than b tells us that c over b is strictly less than 1. So we can write it in a somewhat, we can write in a disregard this last line for now. I'm still over here. We can regard this as write this in a slightly more fancy way, as a over b is 1 plus, instead of c over b, we'll write 1 over b over c, and now b over c is strictly greater than 1. Okay, just bear with me. This is a funny way of writing the same thing. But now what I'll say is, okay, the second equation tells us something about b over c. What does it tell us? It tells us that b over c is 1 plus d over c, but 1 over c over d is just a fancy way of writing d over c. So we can write it like that. And what's c by d? C by d is, no, but what is it equal to? Yeah, it's greater than 1, that's true. And what is the next equation I'd write in this space to the right of this equation? C over d is equal to? 2 plus e by d, which becomes 2 plus 1 over d by e, and this d by e again is strictly greater than 1, but actually d by e is equal to 2. That's what the last equation tells us. There's nothing more, and the process has ended. Now we can take this and put it together. So what we'll do is, this expression which we have for b by c, we'll substitute it over here. So we'll get a by b is 1 plus 1 over 1 plus c by d, and then this expression for c by d, we'll put it in there. So I'll show you what you get. You get this horrendous looking thing. So this thing here is actually, this denominator under the first one is nothing but b by c, and that turned out to be 1 plus, and this is just c by d, and that turned out to be 2 plus 1 over d by e, but d by e is just 2. Okay, yeah. So this system of equations can be equivalently written in this form, and this is a very well, it looked horrendous, but now I'm thinking it looks quite pretty. I mean, it's like these things are all positive integers, and then there's always a 1 over something. So here we've got 1, 1, 2, 2. This is sort of the signature. This kind of a thing is called a continued fraction expansion. So this is called the continued fraction expansion of 12 over 7. And so what you do is, you have a rational number. If it's greater than 1, you write it as, you know, the integer part plus 1 over something which is greater than 1, right? And then you take that, so you had something that was greater than 1, you wrote it as its integer part plus 1 over something that's greater than 1, and now you start with this guy and do the same thing. So recursively you keep doing this, and this corresponds precisely to Euclid's algorithm through these kinds of equations. Okay, so you need to try it out yourself to really understand it. It's hard to kind of get the total complete hang of it immediately. Eventually recordings of this talk will be put up on the internet, and I'll also put up the slides, a PDF file. It's here, so maybe I can ask the organizers to make it available, so you can go over it at leisure later on. So now let's come to a very important theorem of Euclid, which tells us that Euclid's theorem is in some, that his algorithm is actually in some sense always correct. So we've seen this in examples. Now let's just make it. So Euclid's algorithm, if it ends, gives a common measure for the magnitudes a and b. We've already kind of seen this, okay, in using examples. Euclid proved that if this algorithm does not end, then a and b cannot have a common measure. And this proof is very clearly laid out in his Elements, book 10 of his Elements. So it's proposition 2 in book 10. And it says, when the less of two unequal magnitudes is continually subtracted in turn from the greater, that which is left never measures the one before it, then the two magnitudes are incommensurable. Okay, this is just saying that you keep doing this Euclid algorithm, and if always something is left, right, you never get exactly, the shorter length never exactly measures the longer length, and this goes on and on ad infinitum, it never ends, then the two magnitudes are incommensurable. So what it says in some sense is that Euclid's algorithm will work if there is a common measure, and if it doesn't work, well, it's the only reason it's not working is because there is no common measure. Okay, and this possibility that there is no common measure is itself somewhat, it's not clear why. Could you actually find two magnitudes for which there is no common measure? That's something that was actually not understood for a long time, and it was quite a sensation when people realized that you can find such magnitudes. So I hope you understand the theorem. I mean, don't bother too much about the way it's written here. I'm just quoting verbatim from Heath's translation, but what it says is that, you start with two magnitudes, you keep doing this process which I described to you, and if it never ends, then there's no common measure, and we know that if it ends, you found the common measure. So let's try to understand this theorem. So here we have two measures, a and b. A is the blue one, b is the red one, and let's try to measure out a in terms of b, and we are left with, so b goes into a 2 times and the remainder is c. Okay, so now what can you say about c? So the first observation is that c must be less than half of a, because if c were, so we are assuming that b is the shorter of a and b, because if c were more than half of a, then certainly b would be even smaller than c, so you could take out b again from c, and so you would that means that's not the correct c that you want. Okay, so we've chosen c to be what's left when you can no longer take out any more b's. So c is definitely less than half of a, so c is like much smaller. And the second, so the point is that if you keep repeating Euclid's algorithm, you write down a, b, c, d and so on, then these terms, every term is less than half of two terms before. So these terms will keep shrinking half and half and half and half, and Euclid actually proves this, that if you have a sequence of magnitudes, each of which is less than half the previous one, and you have any other magnitude, so we have this the wall of this auditorium, a large thing, and we have this computer monitor here, a somewhat small thing. But suppose we now take a sequence of magnitudes. The first is the wall of this auditorium, and the second is something which is less than half as long as the wall of the auditorium, and the third is something that is less than half as long as the second, and each is less than half as long as the previous one. Then after a finite number of steps, you will have something that is smaller than the width of this monitor, or even smaller than the width of this pointer. So that was something that Euclid actually proved from axioms, but let's not be so, there's always time for that later if you like. So the point is that because of this, the magnitudes that you get from Euclid's algorithm, they diminish to become smaller than any given magnitude. So these remainders that you are getting will keep getting smaller and smaller. And the other important point is that the common measures of A and B are the same as the common measures of B and C. One way is quite clear. Suppose you can use something to measure C and you can use it to measure B. Then because A is composed of a certain number of B's and a C, you can use it to measure A as well. So suppose there's something called D which goes 2 times into C and say 4 times into B, then it will be 4 plus 4 plus 2, 10 times into A. And the other way is also pretty clear. If something measures A and it measures B, then it also measures C, because you measure out A and then you kind of work backwards. You de-measure sort of A along B. It measures B, so a whole number of times it will come back, and so then it will also measure C. So the important point is that the common measures of A and B are the same as the common measures of B and C. So if you're looking for common measures, you lose nothing by passing from the pair A comma B to the pair B comma C, and then you lose nothing again by passing from the pair B comma C to the pair C comma D, and again and so on. Okay, so these are the two important points in the proof of Euclid's theorem. So let's give the proof. So suppose that, so what do we want to prove? We want to prove that if this algorithm never stops, then A and B have no common measure. Okay, so what we'll do is we'll say, suppose they do have a common measure, then the algorithm must stop. Okay, this is called a proof by contradiction, or if you know Latin, reductio ad absurdum. So so we'll do that. So we'll say, suppose that A and B have a common measure, and what better name to give it than X. Okay, so let's call it X. Okay, so X is a common measure of all these magnitudes A, B, C, D that we get by applying Euclid's algorithm. Okay. On the other hand, these things will diminish to become smaller than X after a finite number of steps, because C is less than half of A and E is less than half of C. So they'll diminish to become smaller than X eventually. But then how can X measure them? You can't measure, right? You can't measure something bigger, something smaller using a big measure, right? So that's a contradiction. So it's a very simple proof actually based on those two observations. Okay, and let's come back now to rational numbers. So we've already observed that if A and B are commensurable, then A over B is a rational number, and if A and B are not commensurable, then it turns out that A over B is an irrational number. So the first thing we've already seen. What about the second thing? So we can again prove this by contradiction. If A over B is a rational number, then so A over B is P over Q, where P and Q are integers, and then well, doesn't matter if they are co-prime or not, but we need to show that. So what's the common measure? Okay, I'll let you think about that. Okay, so okay, on the other hand, we've also seen the connection with continued fractions. If Euclid's algorithm ends, then A over B has a finite continued fraction expansion. We saw that. You can write down the continued fraction expansion from Euclid's algorithm. Otherwise, this continued fraction expansion that you write will keep going on. You'll get more and more terms. Sorry? Yes, it'll be infinite. It'll never stop. This process is recursive, and you stop when there's nothing left. So that it'll keep going on. And so we can reinterpret Euclid's theorem in the following way. Rational numbers are precisely those numbers which have finite continued fraction expansions. So if you want to know if something is rational or not, you just have to know if it has a finite continued fraction expansion or not. Okay, so so we'll use all this to prove one of the first really non-trivial theorems of mathematics. Well, maybe Pythagoras' theorem is a theorem that is before this and also very important, but this is where somehow number theory really starts. So so this is a long statement. Let me read it first. If it gives you a headache, don't worry, just close your eyes and take deep breaths. The squares on straight lines commensurable in length have to one another ratio which a square number has to a square number. So what are you doing? You're taking two magnitudes, say your two sticks, and you draw squares with, so maybe if we had given you 4 of each type of stick, maybe 4 of you can get together, you can draw squares with a big square and a small square. Now these sticks which you've got are actually approximately commensurable, okay? So then what you're saying is that you look at the areas of the squares that you get from these sticks, they will, if you look at their ratios, they will be the ratios of square numbers to square numbers, like 49 is to 16. Okay, this is not the interesting part, just to get warmed up. And squares which have to one another the ratio which a square number has to a square number also have their sides commensurable in length. So it's saying that if you have a square whose area is, say, 60, you have two squares and their areas are in ratio, say, 64 is to 49, then we know that their edges are in ratio 8 is to 7. Okay, so that's again not a big deal. So this is, okay, Euclid is just warming up to get to the interesting point. But the squares on straight lines incommensurable in length do not have to one another the ratio which a square number has to a square number. So if you take two sticks which are not commensurable and you look at their squares, then they may have a ratio like 3 is to 1. Okay, so 3 is to 1 is not a ratio of square numbers. No matter how you write it, you can write it as 9 is to 3, you can write it as 48 is to what is something. Okay, so 16. Yeah. So but you'll never get a ratio of square numbers. Okay, that's also okay. So when is Euclid going to get to the point? And squares which do not have to one another the ratio which a square number has to a square number also do not have their sides commensurable in length either.
Yeah,
obvious?
I mean, yeah, the square.
Okay.
Okay, wait. Obvious.
So let's think about this, because to me this is the only thing in this big statement which is not obvious. So what Euclid is saying is, suppose you have two squares, but their areas are not ratios of square numbers. So you have something like a square whose area is 3 and a square whose area is 1. So
Okay, I got the square number. Yeah.
then their sides are not commensurable. So if we have a square whose area is 3, what's the length of its edge? Root 3. And so it's saying that root 3 and 1 are not commensurable. So in fact it's saying that the square root of any perfect square, any number which is not a perfect square is irrational. And this is really the gem in here. And so let me just illustrate this last point with the simplest example. So I want to construct two magnitudes which are incommensurable using that last point. So let's just look at this. We have a square whose side is of magnitude b, and we draw a diagonal and call that a. Okay, so what does Pythagoras theorem tell us? So that's a b, that's a b. So Pythagoras theorem says that the sum of the squares a squared is 2b squared. A is equal to root 2 times b. Let's write it in the squared form. A squared is 2b squared. So the squares of a and b do not have, using Euclid's language, to one another a ratio which is a square number, right? 2 is not a square, 2 is to 1. It's not a square number. Okay. So Euclid's theorem says that a and b are not commensurable, or in other words, root 2 is an irrational number. And I'm sure, how many of you have seen a proof of this? Yeah. Well, no, a proof is a proof, so. Okay, so many of you have seen proofs. Let's see if this is tell me later if this is the same proof or a different proof. No, I mean it could be the same proof with pictures. So let's see if it's really the same proof or a difference. So what I'm going to do is, I'm going to start with root 2 and try to find its continued fraction expansion. So what do you do when you want to find a continued fraction expansion? You take this this number, and remove its integer part. So what's the integer part of root 2? It's 1. So we have 1, and then we have root 2 minus 1, and we know that root 2 minus 1 is between 0 and 1. And so we can write it somewhat fancily as 1 over root 2 minus 1. Okay, no problems there. And now let's work with this 1 over root 2 minus 1. So what is 1 over root 2 minus 1? So root 2 is like 1.4 roughly. So root 2 minus 1 is roughly 0.4. So 1 over root 2 minus 1 is a little more than 2. Right? So it should be 2 plus something. Okay, so we'll just take a 2 plus, and this thing here is between 0 and 1. Okay, and now this is why I had to prepare slides, because I'll always make these silly mistakes while doing these simplifications. So if you take this thing and take the common denominator as root 2 minus 1, then you'll get 2 times root 2 minus 1, and you bring that up here. That minus 1 becomes a plus because there's a minus in front of the 2. So you get 3 minus 2 root 2. And 3 minus 2 root 2 amazingly turns out to be root 2 minus 1 the whole squared, because root 2 minus 1 the whole squared is root 2 squared plus 1 squared minus 2 root 2. So you can simplify that to 2 plus root 2 minus 1. And now this, we do the trick of writing root 2 minus 1 as 1 over 1 by root 2 minus 1. So we do that. But see, now nothing new is going to happen now. We are still, this thing, it's just the same thing. So we do it again, we'll get a 2 plus 1 over root 2 minus 1. And this will go on indefinitely. So what you have here is that the continued fraction expansion of root 2 is not going to end. The same thing will keep repeating. It's never going to change, right? So it's never going to end. And so root 2 is actually irrational. Is this? No? Okay. So this may be a new proof for some of you. It's not the first proof that I saw. So in my book we had a proof that suppose root 2 is a over b, then you square it and you divide by 2 and some clever stuff like that. So this is also very clever, and this is actually not from Euclid's book. This is just observation I made. So that's, I think this is a nice point to sort of stop talking and let you think a bit. So So what I want you to do is to just try to make sure you've understood Euclid's algorithm. So for that I have given you two sticks, and very carefully see it's sort of broomsticks which I cut with scissors. Bought a broom in Tiruvanmiyur market this morning, and there may be some slight errors. So if your things match to within half a centimeter, you assume they match, okay? And here's what you have to do. Let me come to the example. So here's you have to do this. So you have a short stick and a long stick, and don't start yet. Wait. So what you have to do is you have to measure the short stick out, and you keep a pen and paper ready, and you have to remember which stick is A, which stick is B, and all that. And you're going to lose your A once you break it. So just be very careful. So it's a bit difficult, and of course you can go home and try it again with. I have some broomsticks left too, so you can cut broomsticks and play with it. So what you need to do is write down these equations as you get them. Okay. So you keep taking the shorter stick and measuring out the longer stick. Now keep track of which stick is your A, B, C, and D, and you won't have the first stick, so you can't trace back your things and so on. So it's very confusing. And what the first person to give me a stick which is the common measure and to tell me what the ratio is.
You have to break it.
Yeah.
You have to break a bigger one.
Huh?
Bigger one. You have to break a
Yeah.
bigger one.
So you have to take the smaller one, measure out see how many times it goes into the bigger one, and see what's left. And you'll get a even smaller stick than the shorter one, right? That's what we saw. Now you take that and go into the smaller one and see what's left. So when you do it the first time, let's not make haste. Let's do this very carefully. So let's just remember. So you have a small stick called B and a big stick called A. Okay, you only get one chance because three of us got tired of cutting sticks for all of you, and we had to do it with this blunt pair of scissors. So and measure them correctly and so on. And if it matches within half a centimeter, consider it done because there could be slight errors. So you have A and B, then you calculate firstly C, you write down the equation. A could be 2B plus C, 3B plus C, or just B plus C. Then you try to measure out B in terms of C. Then you get D, you try to measure out C in terms of D, you get E, and keep doing this till something exact happens. You'll be writing down these equations, and then you'll be working backwards to give me, and you'll also have this little stick left. And the first person to give me both these pieces of information, there used to be some chocolate over here. Oh, okay, will get some chocolate from Kamalaksha. Yeah?
How is supposed to break it?
Yeah, so doing mathematics needs skillful fingers. So take your, it's sort of, your trade-off between speed and care. So if you mess it up, that's it, you're finished. And if you do it too slowly, well, somebody may beat you to it. But I think he has more than one chocolate, so. Okay, you can come over here and tell me the secret numbers. You got it? Well, why do you come over here? Don't tell everyone. Yeah, write it down. Okay, write it down and bring it here. Hey, you have to work it out as well. No, just bring it. But you have to write down the ratio. See, you have to do this, solving the equation. That's okay. If it's 0.5 centimeter, that's okay. It's not quite right. But where's your little leftover stick? This one? This is the last stick? No, that's not it. Let's see if, I hope somebody gets it. Otherwise, maybe our sticks were just not cut precisely enough. Right. Where's the final answer?
I got the smaller stick as 2.6.
I got it 18.
And I got a D as.
No, you have to tell me only two things.
Yeah,
You have to tell me what is A is to
I
B.
got 18 is to 11.
3 is to 2.
Okay.
Sir, 8 is to 5. 3 is to 2.
Yeah, and where's your stick? But you just measured it.
Sir,
Where's your 1 inch stick?
sir, we have to cut it, sir.
Yeah. How do I know you didn't measure it with a ruler? Oops, sorry. Huh?
Okay.
No, it's not exactly so. No.
Someone have a scale here.
Well, maybe you should hold on to your sticks because I want two pieces. I want the little stick and I want the ratio. If either one is missing,
Mine, this little stick was somewhere here.
this one, yeah. But your ratio you didn't. No rulers.
No, measuring.
No. You have to tell me the ratio by solving the equations.
18 is to 11.
You have to give me the little stick.
Yeah, I got 18 is to 11.
No.
8 is to 5. 8 is to 5.
Where's your little stick? This is your little stick? This is your little stick. Okay, I think we have a winner here. Okay, so you all,
The book here.
you have it written down? Okay, so we have, okay, I think, huh? Okay, we'll take, huh?
Sir, I got 3 is to 2.
No, okay, so we'll stop with two winners here. We have two winners.
What's the answer?
Huh? 8 is to 5 and the,
8 is to 5.
okay, but
8 is to 5, sir.
only two winners, so you and,
First, second, third, sir. First, second, third, you can take note.
I don't remember who's third, so we'll, I was going to give only one, yeah, but you measured it with a ruler.
Sir, no, sir.
You didn't even break your stick.
Sir,
You have to give me the little stick. That is the rule.
Sir, this is a little
Okay, game's over.
Sir.
Sir,
If everybody wins, it's not an interesting competition. So we have two
8 is
winners.
to 5. I got it.
Why don't you come on the stage?
Sir, please, sir, you can take third.
Oh,
This is fun doing it.
yeah. So, hey, who has the chocolates? So, Kamalaksha will distribute the prizes. And we have Aniraj, Neeraj and Shweta. Yeah, you please. Okay, so no, I think after that I lost track. There were like so many people. So these were the first two. I hope I was reasonably fair here. It's always I wasn't quite prepared for the response. So thank you all for listening to me, and I hope that you will go back and try to look at this book. You can also look at Hall and Stevens. That's a edition for schoolboys with a lot of exercises which they call riders, which was used to torture boarding school boys in England for 100 years ago. So thank you very much.